found galaxies, including our Milky Way galaxy. He's been an advocate and developer of scientific education for all ages, and he's written 3 books: Astronomy, a Beginner's Guide, Milky Way, an Insider's Guide, and Galaxies and the Cosmic Frontier. So please welcome our very own Phil Wallen. All right.
Thank you, Elaine. I like that idea of an expensive education. Actually, I stuck with state schools, so that was helpful. And I recommend it to others. So let me share my screen.
Middle bottom.
There it is, okay. Oh, you have to enable me in
Oh, bummer. I didn't do.
actions.
I knew I'd mess up somewhere. It was just a question of where. Hang on.
Tell me when.
It'll tell you.
Okay, so share screen. There you go. Okay, so here I am. And share. And I'm going to do the slideshow. Oh, what's this?
That's fun.
Okay. All right, so that's it.
Let me cut your lights a little bit. Go ahead.
Okay, so there was a meeting recently of the American Astronomical Society. They meet bi-yearly, so 2 times a year, and the winter meeting is the big meeting. And this society is the largest society of professional and student astronomers. So when they meet, they have a lot to say. And this particular meeting was held in New Orleans, which I did not go to. It would have been nice to go in January, but I did not go. But I posed as press, which I can sort of get away with, and that got me access to basically the only online portion, which were the press conferences, and they give you all the materials as well, the press releases and the videos and the slides. And so I was able to piece together this presentation on some of the press conferences that I thought were really good. There were 8 days of it. Sorry, there were 8 press conferences and 36 presentations all told. And I've culled about 16 out of them, so that's like 30%. My biases in some ways had to do with pretty pictures and whether or not I understood what the heck they were talking about. Okay, so let's get started. We're going to go from nearby to far in this sequence, and so here we go. All right. So we'll start off with planetary presentations. The society has a division of planetary sciences, the DPS, and they have their own meetings. So this overall astronomical meeting does not feature very many planetary presentations by what I mean solar system presentations. So yes, there were planetary presentations, but they were not in our solar system. They were of other planets. And so let's get started. We start with WASP 69b. It's a planet, and it goes around a star, and they find that it has an atmosphere that's escaping to produce a tail, which you can see rather easily here in this artist's conception. It's like a planet with a comet's tail, and it's evidence of its atmosphere photo evaporating and extending away from the planet. And this is by Dakota Tyler, and he's at UCLA. And so here is the star. You can see the big yellow thing is the star. That's WASP 69. Come on. WASP 69, and it's about the same mass and size as the sun. 8/10 of a solar mass, 8/10 of a solar radius in size. The planet is a little less than a Jupiter. You could call it a super Earth or a sub-Jupiter, a third the mass of Jupiter, but its size is more closely that of Jupiter. It has a radius of 1.1 times the radius of Jupiter. So you can imagine it as being a rather fluffy object. It's got an extensive atmosphere already. The key thing is the period. It goes around its star every 3.9 days. Okay, so we go around our sun every 365 days, last I checked. And so this thing is very close into its star and it's getting baked by the star. It's and as a result, its atmosphere is heating up to the point of escaping, reaching escape velocity. And that's called photoevaporation. And this planet is losing its atmosphere in real time. So that's the story here. And what they did was they have access at UCLA to the Keck telescope on Mauna Kea, Hawaii. And that's a big ass telescope, which has a lot of light collecting area, multiple mirrors. And they used a spectroscope to track it, to monitor it. And you can see that they were monitoring a particular line of helium, a helium absorption line. And in transit, the star's light is passing through the planet, passing through the planet's atmosphere. And it picks up this absorption by helium in the atmosphere. And so you can see that during the transit, this is the period of transit, there's a lot of absorption at this wavelength, just a little blueward of, I think this is where it should be, the nominal wavelength, laboratory wavelength. But then what happened was after the transit, it was still absorbing. And so that means that it had an extended material beyond the planet that was still absorbing light from the star. And notice that it's at bluer wavelengths, shorter wavelengths. So that tells us that it's coming towards us, blue shifted, it's coming towards us at around 23 kilometers per second. That's pretty fast. The escape velocity from Earth's surface is about 10 kilometers per second. And this is just one component of the velocity towards and away from us. And they estimate the mass loss rate, it's not much, it's an Earth mass per billion years. But that's, you know, you wait a few billion years and it adds up. So here are artist conceptions, and you can see on the left-hand side, the planet post-transit, I believe. Post-transit, here's the planet, here's the star, and you can see there's still some schmutz absorbing light from the star, and in particular, the helium in this gas has a very particular absorption at a particular wavelength, which they could track. And on this side is like a God's eye view of the system with the planet in orbit around the star with the cometary tail. It's interesting to me that, you know, when I think of a comet, the tail should be kind of going this way, away from the star. But that's the plasma tail. This one seems to be following the orbit of the planet more. And that would be like the dust portion of the tail of a comet going around the sun. But it's just an artist's conception. I don't really know how much veracity this has. Okay, so that's planet number one. Planet number two is not even a planet. It's a brown dwarf, but that's like an almost planet. And I'm gonna just get rid of something here. And so this was presented by Jackie Faherty, and she does a lot at the planetarium at the American Museum of Natural History. She's a fabulous presenter, has lots of charisma, and she made the case for this claim, this auroral signature, very, very exciting when she was presenting. I cannot do her justice, but I can move on anyway. So to set the stage, on the left, you have a low mass star. That would be like an M-type dwarf star. Have you ever heard of the spectral sequence of stars? O, B, A, F, K, M. Oh, be a fine girl or guy. Kiss me. And but it goes to even lower surface temperatures, and those are the L, T, and Y brown dwarfs. And she gives indications of how hot those surfaces are. L dwarfs are like pottery kilns, so it's maybe upwards of 1,000 kelvins. T's are like lava flows, and then Y span a range of from conventional ovens to a cold day on the North Pole. And then there's giant planets like Jupiter, where it's in a deep freeze. So what she's talking about here are the coldest of the brown dwarfs. So they're really almost planets. So there were two that were discovered. The first one, W 1935, was discovered by a citizen scientist, someone like you, who was working with the Backyard Worlds Project, which is part of that Zooniverse menagerie of citizen science projects, online citizen science projects. So good for him. It has a distance of about 14 parsecs, 50, like 45 or 50 light years away. And W220 was discovered basically by a satellite, the WISE satellite in the infrared. You can imagine these are very dim things, and probably radiating mostly in the infrared. And so the team discovered that one. It also is at a fairly nearby distance, and its temperature is 482 kelvins. That's like about 200 degrees Celsius. So that's definitely warmer than boiling water here on Earth. So I guess you could get an oven up there. And its mass, the masses of these are between 6 Jupiter masses and 35 Jupiter masses. So kind of almost planets, but not quite. So the James Webb Space Telescope was pointed to these two brown dwarfs using a very accurate spectrometer, very sensitive spectrometer. And this is the spectrum which they got of both of the objects overlaid from a wavelength of 3 to 5 microns. So that's kind of in the near infrared. And as you can see, there's a lot of ups and downs. Well, and those actually are features which people in the know what they are. So for example, there's in absorption, you've got water molecules, H2O, ammonia molecules, NH3, absorbing the light from below in the planet. And but that's fine.
Or someone's cleaning it, one or the other.
That's right. It's so easy when you use less oil. And then there's carbon monoxide, CO, and those produce characteristic absorptions, characteristic wavelengths. That's nice. And then carbon dioxide, CO2, another set of absorptions. And so they were happy to see that, to see molecules in the atmosphere of this brown dwarf. And well, what's going on here? There we go. But what they got all excited about was methane. There's a methane in absorption at around 3.7 microns. But what really rocked their world was this methane feature, which happened to be in emission. So that means there was glowing. This planet, sorry, this brown dwarf is glowing in the light of methane. But just one of the brown dwarfs, it's the W1935 rather than W2020. And you can see the methane in emission here contrasted with maybe an absorption signature of methane. I'm not too sure about it. It's kind of in the weeds, but they very excited about this methane in emission. And so this is not the brown dwarf. This is Jupiter, seen on the left in the visible. And what do you see near the pole? An aurora. And it's due to its moon, Io, which is very volcanic, and it's spewing sulfur, which ends up becoming ionized, and that gets entrained in Jupiter's strong magnetic field and gets funneled to the poles, where it slams into Jupiter's atmosphere and produces an auroral emission. On the right is a Webb picture, Webb image of Jupiter, where you can see in emission methane. They figured that out at the poles, probably for the same reason. So there's a cause, and so this is probably a precedent for what might be occurring with this methane detection in emission on that brown dwarf. So her conclusions are that they both show rich chemistry in the spectra near clones, but this one particular brown dwarf showed methane in emission they've never seen before in a cold compact object outside the solar system. And so they speculate that there's an aurora going on somewhere on this brown dwarf, which is emitting in the light of methane. Now, this is a lonely object as far as we know. It's not like the Earth and the sun where we get aurora. Why do we get aurora? It's the sun and its wind, which interacts with our magnetosphere, and stuff happens near the poles to produce aurora. This one's not near a star, but maybe it has a moon which has not been detected yet, which is doing similar things like what is happening with Io and Jupiter. But they don't really know. So that's kind of fun. It was a great presentation. Okay, so we move on beyond planets and solar presentations. The American Astronomical Society also has a division, a solar division. So again, most of the solar presentations occur elsewhere. And there were two that made it to the press conferences. One of them were gamma rays from the sun in an asymmetric distribution from the sun, and I just didn't understand it. So I'm not going to present that. But this one I could understand. It's our sun through a new lens, and it's a catalog of a new kind of solar flare, hot thermal solar flares by Aravind Valavan of UC San Diego. And so he gives a little description of what solar flares are. They're randomly distributed on the sun. Actually, they occur in 2 latitude bands most times. And they emit clear across the electromagnetic spectrum from the radio waves to the gamma rays. And they last for several minutes to a few hours. And they are the most energetic explosions in the solar system, at least for now. And they produce tremendous amounts of energy, and they have impacts here on Earth. Modern day damage to the electronics that we have on our spacecraft. I think the Starlink failure that happened last year, 2 years ago, where they fell. And satellite communication, you can get disruption in what you hear at radio waves. And then, of course, there's the radiation hazards. They spew a lot of particles at high velocity, and it's really rough on astronauts who happen to be outside the Earth's protective magnetosphere. So they're of interest for obvious reasons. And one optimal way to detect the solar flares is in the X-rays, because they're at high contrast with respect to the rest of the sun. And on the right-hand side, you see basically a timeline of solar flares over a day. That's kind of cool. And they have different energies. They go from, A to X. X are the strongest flares. And so whenever you hear of an X class flare, you might take note and see, duck and see what happens to your service, your internet service, and what might occur up in the sky with aurora.
Maybe it'll knock down a few more Starlinks.
You can only pray.
Wait a second. 10 to the 5th nanowatts per meter square.
That might be 10 to the 9 watts, as opposed to 10 to the minus 9 watts.
No, I didn't say minus,
And NW, I'm not really sure what it is.
but that's a nanowatt
Yeah,
per square meter. Per square meter. Yeah, that's pretty light.
oh, that maybe that's as received here on Earth.
Yeah.
There you go, okay. Yes, and so what causes a solar flare is that there are these regions of strong magnetism on the sun, often associated with sunspots. And the magnetic fields will reconfigure suddenly, impulsively, to lower energy states. And when they do that, they release energy in the form of a flare and perhaps an eruptive prominence or a coronal mass ejection, all this stuff. And so characteristically, the light intensity follows over time an impulsive rise, a very rapid rise. And then as that energy dissipates in the corona, heating the corona, there's a slower decay over time. And that's the typical impulsive flare. But what they've found is a new type of flare by monitoring flares in the X-rays. And on the left, you have an impulsive flare, but on the right, you have what they are calling hot thermal flares. You don't have that impulsive rise. You're not seeing that magnetic reconnection. There's already been dissipation or something to turn the energy into heat. And so they're curious about this different kind of flare. And it has significant statistics. Approximately 25% or a quarter of all flares are these hot thermal flares. And so they're worth paying some attention to. And there's all sorts of questions as to what's going on. Is the two kinds due to variations in the heating rate? Well, is there a variation in the heating rate as a result of how the flare gets generated or propagation of the energy in the medium? And then they're wondering whether there's correlations with other solar phenomena, such as the coronal mass ejections, those big wads that get ejected into interplanetary space, or solar particle events. I guess those are like proton flares, I'm not sure. And they note that the temperatures are really high. They're in the millions of degrees, whereas the sun's surface is only a few thousand degrees. And so maybe these hot thermal flares could be a partial solution to why the corona is so hot. And there's a new observatory coming up, DITIA L1, which may help to answer some of those questions. So that's it for the sun. Moving on to stars, other stars, stellar presentations. Now we get into a pretty big eruption. A coronal mass ejection on steroids, I suppose. Colossal star erupts, examining one of the largest stars in the Milky Way as it fades from view by Narsareti Anugu and the Chara team, which is at Georgia State University. They've actually imaged one of these stars. Why? Well, it's imageable. It's huge. RW Cephei. If it was put where the sun is, it would extend out beyond the orbit of Jupiter. So that's a honker of a star. It's an official classification. This is a hypergiant. And a good analogy would be the red supergiant Betelgeuse. And I'll refer to that a little later. And these type of stars are very typically massive and unstable. And there was a recent eruption. And this is what they saw, that this is a light curve over time, going back a few years. And it was normally bright at 6 or so magnitude. And then it took a nosedive over a few years and became very faint by a magnitude. So that's a factor of 2.5 in brightness. And they were able to catch it with their fancy observatory, which I'll describe, right when it was at its faintest and then back on the rise. And so this was the close-up view that they managed. It's an interferometric array of 6 telescopes, 6 1-meter telescopes. The mirrors are a 1 meter in diameter. And what they do is they take the light from each of these telescopes and feed it through a pipe to this beam combining and synthesis facility, where you end up getting these things called fringes. It's interference fringes. If you were like on the beach looking at the sun through your eyebrows, you might actually get some interference fringes. And there's other examples. An oil sheen on some water will produce interference effects with the sun shining on it. But by combining these beams and getting the fringes and monitoring the contrast of the fringes over time, they're able to get 2-dimensional information that they can basically use to reconstruct an image of the star. And so here are the images, interferometric images, when it was faintest. And you could see here, it seemed to be, there was a region that was fainter on the right-hand side. And then later, 1.5 years later, it was fainter on the upper left-hand side. And they think that, they know why. Something was getting in the way. And what they think was a big, perhaps likely something similar to a coronal mass ejection, a big wad of plasma, hot gas, got blown off of this giant star and started cooling as it got farther away from the star. And as the gas cooled, its refractory elements, the ones like silicon and carbon, they started to crystallize into dust, grains of dust. And once that happens, you now have something that's going to obscure the light. And so here you have a gas cloud that's turned into a dust cloud, at least some of it. And here you see it obscuring the light from part of the star. So it's very similar to Betelgeuse. And I encourage some of you to find RW Cephei the next time you get your big Dobsonian out, and see how it's doing, because it could do it again. I've never even heard of this star before. Okay. So that's an explosion on a star. This is what happens when a whole star explodes. So it, it blew up real good. And the star, well, what we see is the remnant, the supernova remnant. It's called Cassiopeia A. And it's been studied by, I'm gonna mangle this name, Dan Milasjevic. And he's at Purdue. And he's been involved with, again, James Webb telescope observations of this very well-known supernova remnant. And there's good reasons to study it. It's young. We see it about 340 years after its explosion. So what was happening 340 years ago? What's that, 1600s or 1700s? Yeah, and there is some indication that there were some observations of the supernova, of the blast. And it's nearby, relatively nearby. I don't know what they mean by a secure spectroscopic classification. They're pretty sure that it's the result of a massive star that exploded. It's a great case study for how dust gets formed in a blast like this and how the dust can get obliterated as well by the energy of the explosion. There is a neutron star, the remnant core of the star, and it's been observed across all sorts of wavelengths with all these NASA facilities. So here is the picture. It's wow. And this was with the Webb telescope's mid-infrared imager. I don't remember what the R stands for. And what was new was this stuff which they have labeled dusky circumstellar material, and that glows at the longest wavelengths. That's due to dust associated with probably gas which is not even ionized compared to what you see in the visible, which would be ionized gas. And then they've identified material which involves a reverse shock. So you have this blast wave that goes out, interacts with the interstellar medium, it produces a shock wave, forward going shock wave, and there's a bounce that goes back, and it's a reverse shock wave. And then they couldn't help but notice this quote unquote green monster, and what that means is it's got a lot of emission at 12.8 microns, I'm guessing is what that is. And that was a puzzle to them, and so they investigated further. This is the near infrared camera's view, and you can see on the outside there's this haze, which is what you can see like with the Crab Nebula, and that haze is due to synchrotron radiation, a different kind of radiation, which is from electrons zipping around magnetic fields at close to the speed of light. And what else did they see? Probably seeing ionized gas in the interior there. But I just want to also have you see this thing. They think this is a light echo, which means that I think this might be the neutron star, I'm not sure. That there was the initial blast 340 years ago, and its light traversed 340 light years and encountered some stuff in the interstellar medium and lit it up, and that's called a light echo. And you'll see a detail of that. So they ask what the green monster is, but you can marvel at all the structure. There's a fair amount of ring-like structure, but it's kind of a mess. And why is it at this particular wavelength? And what they think is that it's part of the shell surrounding the neutron star, which is in front of the star. It's and it's getting heated by the forward shock. Now, I don't know why they came to that conclusion, but I guess they eliminated other possibilities. So that's what they think the green monster is. And then there's this. This is the light echo. So this is just some random piece of interstellar medium. It, you know, it looks like something out of the Alien. And there's a lot of structure there. Could it be orchestrated by magnetic fields? They don't know. Is this characteristic of the interstellar medium at high resolution? They don't know. It's kind of exciting. So that's it for Cassiopeia A. Okay, we're getting galactic. It's mostly galactic center. And I'm showing this, but basically there's just one image, which is low. This is not the image. I mean, it's an artist rendition. But and she focused, Natalie Butterfield's focused on a dust ring in the galactic center or near the galactic center with an instrument and a project called the Far Infrared Polarimetric Large Area Central Molecular Zone Emission Legacy Survey. I like the way they pick what letters they want to use for the acronym. This is the picture I want to show you. It's the nuts. And it's at multiple wavelengths, mostly in the mid and far infrared. So let's start with the purple. That's pretty warm dust. It's been warmed by bevies of hot stars, newborn stars. So, and that's along the Milky Way. And the 250 micron in teal seems to be concentrated at this brick and in Sagittarius B2, which is a well-known molecular cloud within a degree of the galactic center. If you want to search for exotic complex molecules, that's a place to go. And then there's yellow. This is radio emission, longer wavelength emission, about a centimeter. And you get this emission called the radio arc, and all these I don't even know what to call them, these threads, that's what they call them. And indicating strange activity near the galactic center. The actual galactic center where the supermassive black hole is right here, Sagittarius A star. But she focused on this little ringy region in the teal. And she used the Stratospheric Observatory for Infrared Astronomy, SOFIA, which is an airborne observatory, which is now mothballed, alas. I think the James Webb Telescope ate up its funding. So using that telescope, she could actually map the polarization of the light. Now, some of you might have polarizing glasses. Well, the interstellar medium can do the same thing, especially if it's composed of dust grains which are oblong and are rotating and aligned with the magnetic field. So that's the model. Okay, if you have a bunch of this dust which is aligned its axes of rotation with the magnetic field, you end up starting with unpolarized light from a star, and it will only transmit polarized light in one direction, vertical here. Now, light from other stars can hit the same material and scatter off of it, again eating up one polarization and leaving light with the polarization in the other direction. They use this model to interpret the polarization that they map. And this is what they found. They found that in this area, that the polarization and hence the magnetic field seems to be in a circular arrangement. And one might ask why. might have something to do with this supernova remnant and the same logic. And this is the logic that they use. You have a star, ambient magnetic field, and then the star blows up and the shell expands into the interstellar medium and takes the magnetic field for a ride. It's frozen in to the plasma that's expanding. And eventually you'll get a swept up magnetic field, which looks somewhat like what they saw. I like this model because I can understand it. You know, nice, simple cartoon. So, okay, the second galactic presentation was by Jay Lockman of the National Radio Astronomy Observatory and its Green Bank Observatory in West Virginia. And he is a veteran astronomer, been around a long time, and he's been very much involved with this telescope and what it can do. It's a very sensitive telescope. And this is what he did not find. This is for you, Elaine. M82, yes. This is a starburst galaxy, or as some of you might say, a status galaxy. And it's a galaxy which is totally in the throes of blowing out material in a bipolar manner. So the galaxy itself is this blue-white stuff. We think it's a disk galaxy seen edge on. And the red stuff is emission from hydrogen, ionized hydrogen, which has been photoionized by the starburst inside, an orgy of hot stars that have been formed in the heart of the galaxy. And so this outflow is so great, on the order of what is it, 1 million solar masses a year. I mean, it could completely use up its interstellar medium this way by blowing it out. Excuse me. But what they found were neutral atomic clouds of hydrogen, and quite a few of them. I think he says somewhere later, was it around 30 or so? These are the green things in this artist's conception. And this is amid this purple haze, if you will, and that's like the X-ray emission from the hot plasma that's blowing up, because there's a lot of supernova activity associated with the starburst. And more recently, they've discovered what coded here in blue, molecular clouds, which I'll just touch on later. And they're going for a ride, and they're probably getting shredded. And so here's the analogy he used, that on the left you have a leaf blower, and there's stuff coming out of the leaf blower, some gas coming out of the leaf blower, and it's having an effect on the leaves. And the leaves are being taken for a ride. But you can't tell the direction of the flow well, whether or not it's collimated. Whereas for the snowblower on the right, you can see that it's a very collimated flow. And so he says, combine these two images, and that's a pretty good analogy of what he thinks is going on. Here is a model of what they think they're seeing. They see some material is coming towards, it has a component of velocity towards the sun and Earth, and that would be blue shifted atomic hydrogen emission. And then there's some of the emission that is red shifted, and that's part of the material going away from us in this biconical outflow. And it's a pretty zippy, on the order of 200 kilometers per second. That's nothing to sneeze at. But even so, yes, 300 hydrogen clouds. I was off by a factor of 10, sorry. Even so, it's not that great a mass loss, 1/10 of a solar mass per year. But the velocities are high, and it might be a transitory phase. The clouds are getting shredded, And now they have evidence for the molecular gas courtesy of this radio telescope in the Atacama Desert, Apex. Well, there's a lot in store. Now that they've seen this outflow, they want to get a better handle on it, better mapping with a variety of radio telescopes, both in, let's see, this one's Australia. This one, I think, might be in South Africa. This one's in Chile. This is in West Virginia, and this one's in orbit. So, more to come. Extragalactic presentations. These are whole galaxies beyond our own galaxy. Perhaps you've heard of this dark galaxy. Have any of you heard of it?
Yes, indeed.
Yeah, it kind of came into our inboxes. It's by Karen O'Neill at, again, the Green Bank Observatory. And they were doing a survey, which is what astronomers do, of low surface brightness galaxies. So these are galaxies which are faint. They're just faint on the sky, very few stars lighting them up. And they wanted to get their gas content and the gas velocities, because if you get the velocities, you can determine how much mass is binding those velocities, assuming that it's found. That's typical of a galaxy. And in that way, you can determine the amount of dark matter in the galaxy. So it's a nice thing to do. And they're trying to figure out why some galaxies are so faint. And they've been doing a multi-telescope study with the Green Bank Observatory. The one in the middle, I'm not sure, it might be Nancy in France or Ohio State. And then the Arecibo Observatory before it collapsed. And what happened was they put in a wrong coordinate. The catalog source declination was mistyped. So they just pointed the telescope at the wrong part of the sky. And they found something. And this is it. This is, I believe, emission from hydrogen at 21 centimeters. It has a redshift quite a bit, which they've interpreted as being due to the expansion of the universe. And that places this galaxy, I think at around 55 megaparsecs away. You know, it's out there. And this is a long exposure image of the sky in the visible. Do you see anything?
You can't see that?
There's a little red air glow from our own atmosphere, but there's no there. And so they don't know what it is. It's the dark galaxy. They've been able to ascertain how much hydrogen gas there is. It's like 1 billion solar masses of hydrogen gas. The line width is almost 200 kilometers per second, consistent with a big galaxy going around. And its brightness in the visible is it's at the limit that we have here from the ground. And they don't really know what it is. And it's a lowest surface brightness non-dwarf galaxy because it's a big galaxy. It's isolated, and maybe that's isolation is helping it not form stars. And it might be the first discovery of a nearby primordial galaxy that is yet to really quicken into stars. So that's kind of fun. And then there are the odd radio circles, ORCs. Alice Coyle, UC San Diego, and they have access to Keck as well. And here's, I think, one of the best pictures of one of them. This is a radio picture of one of these ORCs. And there's quite a few of them. I think there's around 11 of them that have been found, mostly in the south, based on this journal that's Australia Astronomical Society, I think. And they're large rings. They're about an arc minute in the sky, about as big as a good sized crater on the moon. And they were discovered by this Australian array. And many of them have galaxies in their centers. I guess follow up in the visible, they've been able to see galaxies in their centers. And with that visible information, they can get photometric redshifts of a z equals a half. And that corresponds to, help me out. You're at a look back time of 4.6 billion years. So we're seeing them as they were about 5 billion years ago. And so their age is around 9 billion years. So they're out there. And they're big, hundreds of kiloparsecs. Origin unclear. Well, with Keck, that big ass telescope, they were able to get a spectrum of one of these orcs. And the spectrum had line emission lines, including oxygen 2, O2. And where's my little cursor? Here we go. Here it is, and the fidelity of their spectroscopy was so good that they could determine that it had a measurable line width, a significant line width, which indicates a high velocity dispersion, which means it's all churned up, whatever it is, and it's very extended. You can see that the mapping is, out to it's about 30 kiloparsecs in size. All this ionized gas, and here's a mapping of it with radius, and compared to what you'd see with just an elliptical galaxy, you're seeing a lot of ionized gas way out there. So what's producing it? And their model is that there's a starburst, back to starburst driven wind, and that produces gas way out there, 40 kiloparsecs. And you're seeing the gas as it's falling back onto the host galaxy. I don't know why they figured that out, but it helps us see outflowing winds after they happen. And so it allows them to see properties of the gas around galaxies on very large scales. So these galaxies are having quite the environmental effect. Okay, we have 2 more, and then I'm done. Cosmic presentations. A big ring on the sky by Alexia M. Lopez from the Jeremiah Horrocks Institute at the University of Central Lancashire. And it turns out that this institute seems completely dedicated to the proposition of finding very large-scale structures in the cosmos. This one got a lot of questions from the press. So she referred to a model of the universe. It's called the Standard Model of Cosmology, the Lambda Cold Dark Matter universe, and it's basically the cosmological principle, which has been around since the steady state theory and the Big Bang theory. They all hinge on it that we're not in a special place in the universe, that you go other places in the universe and it's going to look on average about the same. That makes it homogeneous right here. And then if you look in any direction over here and then over there, it'll still look the same. That's isotropic. And that has been a major assumption, which has led to what is known as the Standard Model of Cosmology. And any structures cannot be any bigger than 1.2 billion light years in size. I'm not really sure how they came at that, but that seems to be the maximum scale of inhomogeneity. Okay, so the first thing they found was the giant arc on the sky. Can you see it? A little Rorschach pattern. No, you can't see it, Michelle? Okay, it's the little smiley face right here. Okay, and So I have to tell you what the gray things are and what the little tiny dots are. Okay, the gray things are galaxies and the little tiny dots are quasars. And they're like big searchlights that shine through the galaxies and the galaxies imprint their absorptions upon the quasar light. And so what they found is that all the galaxies in this arc are at the same distance, about 9.2 billion light years away. And the size is at the distance is 3.3 billion light years. So that violates the cosmological principle. And here's how they figured this out, because I just said they were at the same distance. How did they determine the distance? Well, you have these searchlights, these quasars, their light passes through the galaxy absorbs light at particular wavelengths. And in particular, they were using the magnesium-2 doublet in absorption. And they basically find the wavelength and determine the redshift that way, and then from the redshift they get the distance. And so here's basically a cartoon of the arc. You know, there's some galaxies that have quasars behind them, some of them don't. So you fill it in a little bit. So that's one, and here's basically the same thing again. It allows you to have a 3D map, not just on the sky, but with distance. And more recently, they have found what they call the big ring. Michelle, what do you think? Can you see the ring? Okay. It has a diameter of 1.3 billion light years, but circumference obviously bigger, 4.1 billion light years. And it's again at that same distance, 9.2 billion light years, based on the redshift of the magnesium-2 line. So yeah, they call the quasars spotlights. And but wait, there's more. They're in the same part of the sky. This is the Big Dipper, right, where you arc to Arcturus over here. And this is Boötes. And somebody tell me what the bright star in Boötes is.
Taurus?
We should know this.
Arcturus. Arcturus.
No, that's down
Is
here.
that someone?
I don't know what it is. I'm embarrassed. But it's only 12 degrees from one another. They're about the same size. And she talked about statistics giving 5.2 sigma, which is pretty good as a detection. But she did not describe the statistics. Though I think several of the questioners were trying to get it out of her. So that's all I can give you on this one. Interesting stuff, big structures in the sky. She said that it might be more like a corkscrew in structure, and she's wondering whether we need a new standard model. And one of them would be cosmic strings out there in space, where there's wrinkles in space-time along which galaxies could form. And then the other one was some major event that goes outward to form the ring. I think one of them was Penrose, the other one was Peebles, cosmologist. So big claims require lots more support. And this is the last presentation by Alexander Koshlinsky at NASA's Goddard Space Flight Center. And this is in the gamma ray. They found a cosmic conundrum. This is the gamma ray view of the sky, and this is familiar as the Milky Way. You wonder why the Milky Way is glowing in gamma rays. There's cold molecular clouds. They shouldn't be glowing in gamma rays, but they are because they're getting hit by cosmic rays, and they get excited to glow in gamma rays as a result. And already you can see there's something going on here, this big bullseye over here. And So for background, they talked about the cosmic microwave back. Now, usually you see cosmic microwave background as this little freckling across the sky. But this is what you see before you process the data. You basically see one region which has a greater number of photons per second, and another region essentially cooler by a very small percentage, 0.123%, which is getting fewer photons per second. And they have interpreted that as our solar system's motion around the Milky Way. And so in this direction, that's the direction we're headed. And in this direction, this is the direction from which we are headed. And so it's basically, I wish their color coding was different. We're getting a blue shift here and a red shift there. Sorry about the colors. And it's indicative of our motion of 370 kilometers per second around the Milky Way. They take that out before you see those pretty pictures. And so they thought, well, maybe we could detect a similar anisotropy in gamma rays. And they thought that due to relativistic effects, in quotes, relativistic effects will amplify the signal. And so they expected an amplitude of 0.5% compared to 0.1%. What they found was this. Now, I'm not that convinced because a lot of the bullseye is in the region which they got rid of the data because of the galaxy, the Milky Way. What you can see is the outflow from the galactic center, but they were concentrating on this. They say that there's an enhancement here. And this was from taking all of the data over all of the years the satellite's been up and just adding it all together to get this background. And what they found is the dipole that they found, this anisotropy, is 10 times greater than what they predicted. And they don't really know what's causing it, but they thought they had a clue with a recent mapping of cosmic rays, ultra high energy cosmic rays. And they have an anisotropy on the sky as well. This was taken by the Pierre Auger collaboration. I think a lot of it goes on in Argentina. So they thought, oh, well, maybe they're connected. Maybe they're related. Maybe the two anisotropies are related. Maybe they're causally related. They thought, well, maybe you got to start with the cosmic rays. They'll produce pions, a type of particle, which decay into a pair of gamma rays. But what they found was that process was insufficient to produce the amount of gamma rays that they were seeing. And so their conclusion is that there's some unknown source producing this anisotropy, or yet another explanation altogether. And so that is a cosmic conundrum based on data which I wasn't that impressed with. So a lot of spurious finds, a lot of unknowns. You probably thought that some people had a better case than others. That's science. But these spurious events are just peanuts compared to what's in the GAAC gallery, which I want to show you here. I have to read
That would be the Phantom Stick Man.
the Phantom Stick Man, Dorothy and Toto cluster, the Butterball Nebula, the mysterious lunar number 14, little understood incident from Apollo, and Rudolph I, the antlers of creation. So I encourage you to go to the GAAC gallery and find the spurious objects place, and maybe add some of your own, maybe here. So thank you for your attention, and call it a night.
Thank you, Bill.
We'll have to stop sharing.
I got it.
Okay.
Thank
good.
you.
All right.
All right, Bill, I have a question before the questions start. If that's all right.
Where were you on the night of the fifth?
Well, a comment first. I, for one, am very excited to be glowing in gamma rays.
Oh, I guess you would be.
I would be. That first planet WASP, whatever the number was,
Yes.
would that float in a bathtub like Saturn does? Or would, not does? You said it was fluffy, and I was wondering if it's denser than Saturn, or if there's a way to
It
tell.
might be less dense than Saturn because it had the mass of Jupiter, wasn't it, right? No, it was.
Still in the orbit.
I thought it was
No,
0.8 of the
it was
mass.
a third of the mass of Jupiter, but the size that was 1 point something the size of Jupiter. Yeah, so that would indicate a very diffuse object in its outer atmosphere, so maybe it would float. You'd have to have a very large tub.
Okay. There's a joke here about rings, but that's okay, we won't go there.
Okay. The orcs? There were several rings.
I was thinking bathtub rings.
Oh, okay. Good.
Where was that
Any questions online for Bill?
Where was the interferometer, Bill?
Oh, it's in Mount Wilson, in California.
Ah, okay, thank you.
Yeah, which nearly burned down last summer, was it? They, I think they managed to save all the telescopes. But, but it's a very hard project to do because the tolerances have to be well within the wavelength of light. And this is in the optical visible range of, like a half a micron wavelength. And so the tolerances have to be ridiculously accurate. Yeah. And you have to know exactly how far each of the telescopes are from one another. I mean, within a fraction of a wavelength.
Do they use laser guide stars?
No, I don't think they do.
So they don't do any corrective stuff?
I don't think they do any corrective stuff. This is not active optics that I know of. They probably look for incidences of optimal fringe visibility. I think it takes a lot of patience. This is about the only optical interferometer that's really functioning well. There's another one in France.
Ah,
Yeah, but most of the interferometers that you've heard about, they're all radio interferometers, and they're the tolerances are much more forgiving. Fraction of a radio wavelength, which is on the order of a centimeter.
Hey, Alan, I thought I recognized that chicken. Do you have any questions?
Yes, I do actually. I was about to jump in there. And, I generally don't when Bill does a thing because he anticipates questions so well and he just builds them into the presentation. And if you haven't read Bill's latest book on astronomy, by the way, you should. It's beautifully, delightfully light, deep, heavy reading, beautiful reading, funny. But the question is, you mentioned the reverse shock waves in that first presentation, and I was wondering what were those shock waves bouncing off of?
It might be the ambient interstellar medium.
Okay.
The supernova blows up into a pre-existing medium.
So those
So-
forward shock waves just go until they hit anything at all.
Yeah, I think that's one possibility. The other possibility, well, there's the stellar wind. There was probably the star had a wind and so it already produced stuff out there. And so maybe it ran into what it had already been blown out.
Bumped into itself.
It bumped into itself. Which all blowhards inevitably do.
Thank you very much. Great presentation. Thanks, Michael.
Any questions in the room?
Any votes on what you thought was the most cockamamie presentation?
I was actually very, very impressed. This is the first time since I've been attending these meetings that I've heard a presenter use the word schmutz. And I was very impressed. It was wonderful.
And I'll go dig it.
Yeah.
Yeah.
Get it.
Well, I like the magnitude scale.
Yeah.
You know, you could say it's ass backward, but more correctly, it's back assward.
On that note.
Thank you, Bill.
Thank you, everybody.
Thank you very much. Great night.
Michael?
Okay, any questions anywhere? All right, closing the doors, folks. Thanks for coming.
Have a
Bye.
great night, Michael. Thank you.
Be there in person
Next
next
month.
week or next month.
Cool.
Cool.